closely related to Markov chains is this idea of game theory. So today we're going to take a look at some game theory, specifically with what are called strictly determined games. And first, just kind of introduce this idea of game theory. Game theory is a brand new field of mathematics. It is a branch of mathematics that is all application. It is used in business, economics, social science, and other fields as well, including just how to best play a board game or something like that. But really the most interesting applications are in business and economics and governmental interactions and such. But what the game theory is built on is this idea that we want to make the best decision. We're going to be faced with several choices. We can either invest here or invest there. We can either play strategy A, strategy B, or strategy C. Which strategy is the best strategy to come out with the best case scenario for me? So I numbered that number 1. That should be letter A. And what we're going to look at, number 1, underneath A, today we're going to take a look at what are called two-person zero-sum games. This means there is a clear one winner and one loser. There is a win for one and a loss for the other player. So it's not like we have something that's a win for both parties. It's going to be a win-loss situation, and we want to be on the winning side. And so how do we get on the winning side? Well, we're going to represent the game with a matrix. And the way we set the two people against each other in this matrix is one player is the rows. And the way we represent the player's payoff, how much he gains in his rows, is the more positive an entry is, the better it is for that player. In fact, positive represents a win for that row player. Conversely, against the row player is the other player. The other player is the column player. And if positives are good for the row player, they must be bad for the column player. So he's going to be the opposite. A negative is going to be good for the column player. The bigger the negative, the better it is for the column player, and any negative represents a win for the column player. And so we represent the game with a matrix where each entry represents the payoff, the benefit, for the row player. So a negative entry then would be no payoff or a loss. That would be bad for the row player, good for the column player. So let's take a look at what I mean here with an example game. Let's have a very simple game. Let's say Saul and Joel play a game with a penny and a nickel. Each chooses a coin to reveal at the signal. Now, if the sum of the coins is less than 6 cents, Saul keeps the coins. Otherwise, Joe keeps the coins. So we're going to set up a matrix that represents this game, all the possible outcomes and all the possible payoffs. We'll have Saul and Joe, who could show either a penny or a nickel. A penny or a nickel. Now, if they both show a penny, in the penny spot here, if they both show a penny, that's 2 cents. 2 cents is less than 6 cents, so Saul would keep the coins. He's stolen Joe's coins, so that's a 1 cent payoff for Saul. He's gained Joe's penny. However, if they show penny and nickel, Saul shows a penny and Joe shows a nickel, his payoff is going to be to lose the penny, because that's 6 cents exactly. So he has to pay the penny to Joe, -1 for Saul. And so as you can see, the positive represents a win for the row player, the negative represents a win for the column player. When we get to nickels, if Saul shows a nickel and Joe shows a penny, Saul's going to lose his nickel because that's exactly 6 cents. So Saul is going to be out 5 cents in that game. -5. If they both show a nickel, Saul will also be out 5 cents because that's much more than the 6 cutoff. And so as we can see, the only way Saul is going to win this game is if they both show a penny. Which kind of gets us to this idea of strategy. We could see that Saul should always choose the penny, because worst case is a loss of 1 cent. Worst case scenario, he'll lose 1 cent. However, Joe should always choose the nickel. Because if you look at the nickel option, worst case scenario for the column, remember columns like negative, worst case scenario for the column is -1, as opposed to the penny, worst case scenario is a +1. That would be not nearly as good. So Joe should always choose a nickel, because worst case is he wins anyways. Worst case is he wins 1 cent. Remember, negatives represent a win for the column player. Negative is a win for Joe. In this case, where there is a strategy that's very clear like this, we'll talk about a better way to find that best strategy in a minute. But when there's a strategy that's very clear that Saul should always do this option, Joe should always do that option, we call that a pure strategy game, or a strictly determined game, where there is one fixed strategy regardless of the opponent's strategy. This isn't like rock, paper, scissors. With rock, paper, scissors, if you always pick rock over and over and over again, your opponent's going to figure it out, change his strategy to paper, and you will always lose. So that's not pure strategy, because in rock, paper, scissors, you have to be constantly changing your selection in order to stay ahead of your opponent. Versus with this coin game, there is a pure strategy. Saul should always choose penny. Joe should always choose nickel, and regardless of their opponent, that's going to be the best case scenario for each player. So how do we find the best strategy? Well, here's what we do. What we want to do is we want to find the worst case scenario for the row and column player. Because if you prepare against the worst case scenario, you will be able to create a best case scenario for yourself. So that's going to be our strategy. For the row player, the worst case scenario is the smallest entry. So we are going to star the minimum entry in each row. We're going to find the worst case scenario of each row. Similarly, for the column player, we're going to find the worst case scenario for the column player. Now, the column player likes negative numbers, not positive. So his worst case scenario, we're going to box the maximum entry in each column. What we're finding is the worst case scenario. And if we protect against that, we're going to create a best case scenario for ourselves. What we're looking for is when the starred entry and the boxed entry overlap with each other, because that's going to be the best choice for each player. Now, it will happen on occasion, in fact more often, that the star and the box do not line up on the same entry in the matrix. If they don't line up in that way, we say it's not strictly determined. If it's not strictly determined, we're going to have some type of mixed strategy, like the rock, paper, scissors example. You got to do scissors sometimes, rock sometimes, paper sometimes, and you got to figure out what your mixed strategy is. There's no one strategy, such as always choosing nickel. If it's not strictly determined, that's what we're going to talk about tomorrow. Today, we're just going to look at strictly determined, like this example with the nickel and the penny up above. I do want to put one caveat on the best choice for each player. Actually, I probably shouldn't use a star, because we're using a star to mark the boxes, huh? I'll put it in parentheses at the end. It could be more than one. There could be two places where the star and the box line up, And if that's the case, that's just fine. As it turns out, it will be the same value both times. So you might have -5 in 2 spots with a box and a star. It's the same value both times, so it doesn't matter. You get the same payoff and the same result for both players in that situation. So let's go back to our example with Saul and Joe. We said a penny and a nickel and a penny and a nickel. 1, -1, -5, -5. So first, for the row player, we're going to star the worst case scenario. We're going to star the negative value. Most negative, the smallest value. In the first row, that's -1. In the second row, they're both the same. It's a tie. If it's a tie, we'll star both of them. That's okay. Then for the column player, we're going to box the worst case scenario, which is the biggest number. In the first column, the biggest number is 1. In the second column, the biggest number is -1. Notice they overlapped at the nickel penny cell at the -1. Whoops. I didn't mean for that to disappear. The star and the box overlapped. That is the best strategy for both. And so how we're going to write down our best strategy is Saul, being the row player, is going to have a row matrix that represents his strategy. The first cell represents the first option. That's the penny. He wants to do that 100% of the time, or 1.0. The second entry is going to be the nickel. He wants to do that never. It's never going to be good for him to play the nickel. And so because Saul is the row player, his solution is expressed as a row. His strategy is expressed as a row. Joe is the column player. His strategy is expressed as a column where the first entry represents the first option of penny. He's not going to do that. The second entry is nickel. He is going to do that. So that is Joe's strategy. The first option 0% of the time, the second option 100% of the time. Where they line up, they both overlap at 1. That is called the value of the game. That means in the long run, every game, what's going to happen on average is a result of -1. That means the row player, we always express things in terms of the row player is going to lose 1 cent every time he plays this game with the strategy. And that's his best case scenario option, is to lose 1 cent a game. So what we've got here is this way of finding the worst case scenario. Star the minimum entry in each row, box the maximum entry in each column, and then you can express the strategies for the row player, for the column player, and find the value of the game. What's the expected payoff of the game each time? So let's try a couple more games and see if we can find the best strategy. Here's another game. Let's say the row player's payoff is -1, 4, and then it's 2, 3. So this looks like it's going to pay off most of the time for the row player. The row player's worst case scenario in the first row is -1. Worst case scenario in the second row is a payoff of 2. The column player, we're going to box the largest entry. Worst case scenario for the column player is a box. What you'll notice is the box here, 2 is the biggest entry in the first column, and 4 is the biggest entry in the second column. Where they line up is the second row and the first column. So the row player strategy is to, get the right color here, the row player strategy is to never play the first option. Always 100% of the time, play the second option. The column player strategy is to always play the first column and never play the second column. And that's going to create a best case scenario for both players. The value of this game is where they overlapped at 2. That means each game the row player is going to win 2 units. The column player is going to lose 2 units because columns don't like positive numbers. And so in this way we have found the row strategy and the column strategy in the value for the game, which is expressed in terms of the row player. Now these examples we've seen so far are all 2 by 2 matrices. There's no reason it has to be 2 by 2. It can be 7 by 14 if you want. What we look for is the same exact strategy. In fact, they don't even have to be the same. Let's say we've got 2 options for the column player, option A or option B. 4 options for the row player. You can choose C, D, E, or F. And we want to know what's the best option for the row player, best option for the column player, and also the value of the game. What's going to be the payoff if they each pick a best case scenario? Well, filling in our entries across the rows, it's going to be a -2, 4, 7, 5, 0, -1, -3, 2. Those are the payoffs. Negatives are good for the column player. Positives are good for the row player. So we prepare for the worst case scenario. The worst case scenario for the row player is a small number. So each row we're going to mark the smallest number. -2, 5, -1, and -3. Those are the small numbers. The column player likes negatives. Worst case scenario for the column is a big result. So we're going to box the biggest value in each column. In column A, the biggest value is 7. In column B, the biggest value is 5. And you notice where they overlap, the star and the box overlap in the second row and the second column. So the row player strategy is to never play the first option, always play the second option, never play the third option, and never play the fourth option. Always play the second option because it's always going to be better for him, regardless of what the column player does. The column player only has 2 options. In this case, he could have had more. He's never going to choose the first option. He's always going to choose the second option. And if they both always pick the best strategy for the game, the value, the overall payoff here is 5. It's going to be a win for the row player. The row player is going to gain 5 units per game, whether that's 5 percentage points, $5, $5 million. It's going to be best for the row player with this strategy. That's going to be our introduction to game theory with these strictly determined games. What I want you to get really comfortable with today on the assignment is the ability to take a situation and make a matrix to represent the game, to be able to interpret what the numbers mean. Positives are wins for the row, negatives are wins for the column. The bigger the number, the bigger the win or loss. And also determine the best strategy for both the row player and the column player. If it's a strictly determined game, they'll both hedge their bets against the worst case scenario. We'll mark the small entries for the row, mark the big entries for the column, and where those overlap, that is the best strategy for each player. If they don't overlap ever, that's the conversation for tomorrow's video. For now, come to class with questions, and I'll see you then.